Hi guys, so I am here at my parents' house and I'm recording this video to explain our next section of notes to you guys. I may have to cut it into two videos. It depends on how long I go, but so anyway, this will be part one or it will be the entire thing. We'll see how it goes. All right, well, let me get rid of me and get to our notes. So you guys should be following along and filling in your notes. This is the last section of our notes in our chapter, the very last thing that I have to teach you for this chapter. So this is about looking at the shape of a molecule and determining whether or not it is polar or nonpolar. All right, so here we go. Okay, so first of all, when we're talking about a polarity of a molecule, that's slightly different than the polar bond. So in the past, we had talked about whether a bond was polar or nonpolar back when we did electronegativity. So you can have a molecule that has polar bonds but is still nonpolar. So we're going to be looking at the whole molecule itself and seeing if it is polar or not. All right, well, a molecule is polar. What that means is that it has a side where you have a side of the molecule that has a positive charge and another side of the molecule that has a negative charge. So this happens because the way the electrons kind of move and are positioned. So if you have an area of a molecule that has a lot of electrons, that's going to have the negative side. And then another area of the molecule that is missing electrons, or that work because the electrons are on the other side of the molecule, like then you have another side of the molecule that doesn't have electrons, so that would have the positive side. So we end up with this molecule that has one side that has a positive charge and another side that has a negative charge because of the fact of the way the electrons are distributed in the molecule. All right, well, when that happens, then it's said to be a polar molecule. All right, it is also called a dipole because di meaning two, pole meaning like two poles to it, two charges to it. So a dipole is a molecule that has this positive charge and this other side that is a negative charge. All right, now we can figure out if it is a dipolar polar molecule because we're going to look at the shape. So the shape is going to help us figure that out. All right, so we'll take a look at how we can determine if it is polar or nonpolar based on the shape. So we'll be looking at the five major shapes that we've been dealing with. So originally when we talked about shape of molecule, I think there were like 7 or 8 different shapes. But we're mainly dealing with 5 because when we're drawing our Lewis structures, it's difficult for us to draw an octahedral one or us to draw a bipyramidal one. Those shapes are a little too complicated for us to draw in Lewis structures. So we're going to deal with the main 5 shapes. So those shapes are linear, tetrahedral, trigonal planar, pyramidal, and bent. Okay, so those are the 5 mainly that we're dealing with. Okay, so when we're talking about polarity, any molecules that have a shape that is symmetrical will be nonpolar. Any molecules that have a shape that is asymmetrical, those will be polar. Okay, so symmetrical equals nonpolar, asymmetrical equals polar. Well, just from this, there are 2 shapes that are always then going to be polar because these shapes are always going to be asymmetrical. So those are bent and pyramidal. So if we were together, of course, I would show you these 2 molecule models and we would look at them and we'd say, oh, of course they're not symmetrical. Okay, so when we talk about symmetry, we're talking about more than one plane of symmetry. It's easy for a molecule to have one plane of symmetry, meaning like if we look at it, the left and right sides would be the same, symmetrical, mirror images. Okay, but they have to have not just left and right, but top and bottom be symmetrical. And oftentimes there's 3 planes of symmetry when we're talking about a symmetrical molecule. So when it comes to the shape of bent can never be symmetrical. So since they are always asymmetrical, they are always polar. Our second shape that is impossible to be symmetrical, always asymmetrical, would be pyramidal. So when you're looking at the molecule shape, so of course the last couple of days you guys have been concentrating on determining the shape of the molecule by counting the bonds around the central atom, counting the electrons that are bonded and the electrons that are unbonded, and from that you were able to determine what the shape was. Okay, so once you have the shape, then the next step, it's a 3-step process we have going here, so the 3rd step in this process is to figure out if it's polar or not. So we look and we see a bent shape, so that's going to be polar. A pyramidal shape, automatically polar. Okay, so those 2 always equal polar. All right, but that leaves us three other shapes. So those three other shapes, linear, tetrahedral, and trigonal planar, are sometimes polar and sometimes nonpolar. It's going to depend, okay? So where bent and pyramidal are always polar because they're always asymmetrical, linear, tetrahedral, and trigonal planar can be either. They can sometimes, depending on what's attached to them, be polar, and sometimes, depending on what's attached to them, be nonpolar. So when you have one of these three shapes, you ask yourself a second question, and that second question is, are all the end molecules the same? Okay, so if all the outside molecules are the same, not the center one, but the ones on the outside, then it's considered nonpolar. It would make a symmetrical molecule. A symmetrical molecule then, of course, would be nonpolar. If all the end or outside atoms are not the same, then it would create a polar compound. Okay, so polar compound because they're not all the same. All right, so now we're going to go through and see a couple examples that are the examples there in your notes. All right, I'll try to go slow because you're going to have to write down their shape and then you're going to have to write down their polarity, okay, because we can't determine polarity unless we first determine shape. All right, so here's our first example. Okay, so A, we have CO2. So CO2 has center atom is carbon, so we are figuring out what shape it is first. So it has 1, 2 sets of bonded. There's no dots, so 0 unbonded. So 2 sets of bonded, 0 unbonded make this linear in shape. Linear. Okay, so now we know that to be the case, that this is a linear molecule. Well, linear, here, I was trying to get the pen and I couldn't get the pencil to come up. So here, now I have a pen. Let's see, I can write linear now. I'll just put L-I-N because, of course, this takes a lot of effort. Okay, so it's linear in shape. All right, so then once it's linear, then it's one of the three that we have a follow-up question to ask. Is it going to have the same, or are the outside atoms the same, or are they different? Well, the outside atoms are both oxygen, so they're both the same. So if they are both the same, that makes this non-polar. So I'll put non. Okay. All right, so the shape is linear. Linear, we ask ourselves, are the outside atoms the same? And since they are, they're both oxygen. This is non-polar. Awesome. Next example. All right, H2O. So here's our Lewis structure for H2O. We look at our center atom, oxygen. Our center atom has 1, 2 sets of bonded, and 1, 2 sets of unbonded. All right, so 2 sets of bonded, 2 sets of unbonded make this bent for its shape. Okay, make this bent. All right, bent is one of the two shapes that is always going to be asymmetrical, so is always going to be polar. Okay, so P-O-L, whoops, sorry. I'm trying to make the pen show up and it won't show up in this particular spot. Let me move the knife. There's yeah, anyway, it doesn't matter. Now I got the pen to work, so we're good. Okay, so this is polar. All right, so since this shape is bent, bent is always asymmetrical, always polar. So just to show you, even though it's symmetrical left to right, if we cut this in half like this, then this is not symmetrical top to bottom, so it's asymmetrical. So that would make it polar. All right, next example. All right, get my pen back here. Okay, next shape. Here's our Lewis structure. So our center atom is nitrogen. Nitrogen has 1, 2, 3 sets of bonded and 1 set of unbonded. So 3 and 1 makes this pyramidal. All right, and pyramidal is always going to be asymmetrical. Okay, if we cut this top and bottom, it's going to be asymmetrical. So asymmetrical is always going to be polar. So I'll put polar here, P-O-L. All right. Next example. Okay, we look at our Lewis structure. B is our center atom. Our center atom has 1, 2, 3 sets of bonded. 3 sets of bonded, 0 dots, 0 unbonded. Make this one trigonal planar. I'm just going to put trig here for this. All right, so trigonal planar. So trigonal planar is one of the three shapes that we ask ourselves a second question. Are all the outside atoms the same? And these are, they're all chlorine. And since they're all chlorine, they're all the same, that would make this a nonpolar molecule. Okay, so in this example, that would be nonpolar because it's symmetrical, they're all the same. Okay, next example. All right, so here we have O2. O2 is just two atoms next to each other. Whenever we have two atoms next to each other and that's all, it's automatically linear. So let me put linear. All right, so linear molecule is what we have. So linear is one of our three shapes that we ask ourselves the question, are all atoms the same? So they are both the same, and since they're both the same, that would make this nonpolar. Okay, so the question we're always asking when we're checking for linear, trigonal, planar, or tetrahedral, we're asking ourselves the question, are all the outside atoms the same? If they are, then it's nonpolar. If they're not, then it's polar. All right, here's another example. So these are two atoms once again. Two atoms always create a linear shape. Okay, if it's linear, you ask yourself the questions, are the atoms the same? Okay, H and fluorine are not the same. Hydrogen and fluorine are different. If they're not all the same, then the answer is that it's polar. All right, so this is polar. All right, last couple examples. All right, so we have this example, taking a look at its shape, and it has center atom is carbon. It has 1, 2, 3, 4 sets of bonded, 4 sets of bonded, 0 unbonded, make this tetrahedral. So I'm just going to put, oh, that's a crazy looking E, tet for tetrahedral here. All right, so tetrahedral is one of our three shapes that we ask ourselves the question, are they all the same? They are not. Even though 3 of them are hydrogen, 1 of them is not the same. So they all have to be the same. So since they're not all the same, this would be polar. All right, polar. All right, next example, we have carbon as our center atom again. 1, 2, 3, 4 sets of bonded, 0 unbonded. That makes this also tetrahedral. Let's see if I can control my E this time. Woohoo! Success! All right, now, since they are all the same atom, tetrahedral is one of our three, we ask ourselves the question, are they all the same? They are all the same, so this would be nonpolar. All right, and you can look at these two examples, this one down here versus this one here, and you can see this one definitely isn't symmetrical. You know, if we cut it this way, this weird one that's huge over here sticks out. But this one, if we cut it a bunch of different ways, we'd be able to get symmetry. So difference between polar and nonpolar, of course, symmetrical versus not symmetrical. Okay, so almost done here. To summarize what we have going on, we check the shape first. From this shape, there are two shapes that always give us polar. That's bent and pyramidal, always polar. 3 that we ask a second question. So linear, trigonal, planar, tetrahedral. If that's our shape, then we ask ourselves the second question, are the outside atoms the same? If they are, then we have nonpolar. Or are they different? If they are different, even just one of them, then we have polar. All right, so there are some examples that you're supposed to try in your notes, but you're also going to have examples here to do for homework here on this worksheet that you're going to have. So either way, you're going to get to do some examples now. So you can just do the ones that are on your worksheet, which you will have the VS EPR worksheet to first draw Lewis structures, then figure out its shape, then figure out its polarity. So you'll be doing all 3 parts to that. That'll prepare us then for our lab that we're going to do when we are together again. So the next time we have class, I will be there with you, and we will do our molecule lab. And of course, I'll cover any issues you might still have as a result of me not being here for this. Okay. All right, guys. Well, I shall see you then soon. Bye-bye.